Otherwise, I need to go into retirement. Okay, right. So we've got the east-west frame and the north-south frame. Okay, and what we're saying is, what does the code want us to do? So when we look at it, that it's very common that we break those frames up into 2 dimensions. So from 3D, we bring it into 2D. As I said, we have the capacity to deal with it in 3 dimensions. The package that you're going to use, for example, Master Series can do that quite easily, right? But we're going to work by hand, remember, as far as the exams, tests, and our work is concerned, the majority of the time. So we're going to look for ways that make it easier for us to work by hand, right? Okay, so we can model it as if we've got a wireframe and in 2 dimensions. And this is what the code does. This is what I use to introduce reinforced concrete design when I teach it at the next level, right? At the 3rd year level. So I'm just taking the introduction from this so you know where you're going with your subject, all right? So for example, the code allows you to simplify it into a subframe. So that's frame figure 3, the full frame. You can break it down into 1 level with the columns above and below. Okay, it further allows you to look at 1 beam only, right? So you take the adjacent beams at columns top and bottom, but your focus is on that particular beam highlighted by the red arrow. Then the code also allows you to break it up into continuous beams, which means, and then your moment distribution, which you will do this semester. Calculations look something like this, right? And then the shear force and bending moment diagrams look like that. We have an envelope because we have different loading patterns, and eventually, if we use that approach, then for the columns, we have to calculate the moment using half the stiffness of the beams on either side. So all of this you will cover in the design subject per se. But what I'm trying to get to you is that the 2 are interrelated. Okay, if you don't know analysis, you can't design. All right, what are you going to design? Design, actually, when we say structural design, it covers both the analysis and the design. But the way we present the course, structural design covers more the material side. It covers the properties of the material, how the material will respond in bending, how much of steel is required, etc., etc. Okay, so the buckling in the column or the buckling in the beam, lateral torsional behavior, all of those things come into the design aspect. But holistically, the 2 are one thing. Analysis and design go together, all right? You can't do the one without the other. So that's just a brief introduction into why analysis and how important it is, especially at this level, because we are dealing now with statically indeterminate structures, all right? We are dealing with statically indeterminate structures, so, okay. At the level below this, you did statically determinate structures, okay? And sorry, those of you just on the side, those of you who didn't collect the notes, I'm here again after 9 today, right? And then again next week in the classroom. Sorry, my apologies. Am I coming through clearly to you? Can you hear me clearly? Okay.
Yeah, now, sir.
Right, good. So at the previous level of study in mechanics, what you did is you did statically determinate structures. So you did something like this. For example, you did something like that, right? Okay, and then you determine whether this is statically determinate or not. So your determinacy and indeterminacy, that was your focus, right? That's what you looked at. Is the structure statically determinate or not? You did it for frame, you did it for trusses, you did it for all of those things, okay? You've passed that, we're over and done with. Now we're introducing a new thing to you, the degrees of freedom. In other words, how many ways how many ways can a point move? Okay, so for example, we want to know at the pin, right? So let's look at the pin. Okay, at the pin here, how many ways can it move? What movement can take place at the pin? All right. So what do we know about the pin? Now I want you to think, normally you say, well, a pin allows rotation, correct? In other words, it has two reactions. So it has a vertical reaction, it has a horizontal reaction, which means those reactions won't allow any movement. It will not allow this thing to move horizontally. It will not allow it to move vertically, either up or down, correct? What it will allow is for this thing to rotate. It can rotate in either direction because it's a pin, okay? So for example, if I wanted to detail a connection like that, I could use a steel plate. I have a member coming in, some kind of member coming in. Okay, that's the background line there in the back. A single bolt, are you with me? All right, and this is obviously attached to something. Okay, so that single bolt will allow this thing to rotate. Of course, there must be no friction, etc. So that's 100% pin, right? On the other hand, the roller there, most common example of a roller is under the bridge. You have a bridge deck, and then you have your abutments. I'm sorry, not your abutments, your supports to your bridge. And then you have a connection there, right? That as you get traffic moving over the bridge, right? It's not connected in that direction, it's connected vertically. So it transfers vertical force, but it allows the horizontal movement, okay? So that's a type of thing where you have a roller. Are you with me? So these kind of connections, not 100% perfect. In other words, what we model, but you'll find that in practice, it's a little bit difficult to achieve that. For example, in a steel connection, right? You got a steel column, right? And then you got a steel beam coming into it. Now you got couple of ways of connecting. There's not just two, a couple of them. So first of all, you may have a seating cleat here, right? And then at the end here, you need to fix that beam to the column. So one perhaps way of doing it, if you want it pinned, is to use a cleat like this. So cleat is an angle, right? It's just another name for it. So you put a cleat like this. Now we're looking in plan. There's the beam web. There's the other cleat at the back, which you're not seeing. Put a bolt through there and you bolt into the column. Are you with me? So that would be bolt into the column. Got it? So sorry. Let's set a nice line there. Okay, so that's your column going out that way. So that's the column. You have this, what do we call it? Cleats, right? So these are the cleats here. Okay, and they hold the beam onto the column, if you follow what I'm saying. And this is their single bolt going through. So that would give you a pin connection. Sorry. Right, so in steel we could do it that way. That's again not a perfect pin, but something very close to it. Alternatively, I could use a fixed connection. So for a fixed connection, I could do something like this. Again, I got a column there looking in elevation. And what we then do is we put an end plate onto the beam. So we weld this plate onto the beam. right? And then we connect it with bolts like that. And you can see that this one's not going to be able to rotate so much. But when we look at it through there, okay, then you're going to see that you have the beam. Okay, and behind, sorry, the drawing is a bit crude, but you have the beam and you have the plate, which is welded to it. Okay, and then those bolts in the background. So that's what it looks like. So this gives you more fixed connection. So this one will be fixed. Right, so that's like a fixed connection. And of course, the pin I showed you earlier. All right, so what we're interested in is, we know in reality these are our connections. This is not a perfect fixed either, but it's very, very close to, so it's 90% of fixity or thereabouts. Okay, with some of the modern software, even master series, you can model a connection with a partial restraint. So you can specify that it has fixed 50% fixity or 60% fixity, and you can do that. Right, so this is something we didn't have the benefit of in the past, but now we have all of these advantages in terms of analysis with various software packages. Okay, but let's get back to the focus of what we're talking about today is how many ways can this thing move? How many degrees of movement do we have? So let's come back to the notes. As previously discussed, in analyzing a structure, we break it down into a series of discrete members, all meeting at different nodes. So here I have member 1, for example. There I have member 2. This would be perhaps called node 1, node 2, node 3. So I'm identifying the connection points at the ends, and I'm identifying what goes between the connection, as we call it, members. When the structure is loaded, it deflects or moves. We're interested initially how these joints move, okay? So degrees of freedom. In general, for structures meeting in a plane, there are 3 ways in which joints can displace, all right? So you've got 2 of these are linear, so you can have a horizontal, you can have a vertical movement, okay? And the third is rotational displacement. So here you have a rotation. Okay, the 2 linear displacements can be in any chosen direction. So you could have a something like this, where it's connected in that plane, for example, right? So it's at some angle. It's not a problem. Okay, so it's already at some angle. So your reactions here, if you want to, could be that way or that way, or you may want to know the forces, which is vertical and horizontal. Are you with me? So we just use 90 degrees as a convenience. That's the thing that we just want to highlight. So 90 degrees is just a very convenient way to work, right, from the mechanics side. So to each other in the horizontal and vertical planes. If a joint is free to move in all 3 of these directions, 2 lateral and 1 rotational, it is said to have 3 degrees of freedom. So just looking at this one, 1 degree of freedom, you agree that it can rotate around the pin. How many degrees of freedom do we have at node 3? How many degrees of freedom do I have at node 3? So at node 1, I have 1 degree of freedom. In other words, it can rotate about the pin. At node 3, how many degrees of freedom do I have? Can it move vertically? Can member 2 move vertically when it is connected to a roller like this? Come guys, you've passed mechanics.
No, sir.
Can't, right? So there's a vertical reaction here, right? Okay, so there's no vertical movement possible. That's out. Doesn't exist. Can it move horizontally?
Yes, sir.
Yes, correct. I heard somebody saying it in the background. It can move there. So I've got 1 degree of freedom. Can it rotate about that roller?
Yes, sir.
Yes, correct. So I've got, that's 2 degrees of freedom, right? So I've got 1 here, I've got 2 there. Now what about this corner? If I put a load like that, what's going to happen? If I put a load like that onto that column, what's going to happen? Member 1 will go to the right. You agree? Member 1, so let me just put the movement. in green. Right. So member 1 is going to move to that position. Okay, member 1 is going to move to that position, and then member 2 obviously is going to push out and go that way. So you're going to have a displacement here, right? Which we agreed on already. There's a displacement. So you follow what I'm saying, right? So this thing has 3 possibilities. It's going to move horizontally. It can move vertically. There's nothing preventing it. There's no support there, right? And it can also rotate, and you see that it rotates. So it's going to do something like that. Are you following what I'm saying? So it's going to maintain it at that intersection because we've got a rigid connection. It'll keep the angle between the 2 members, which means the beam has to bend down to accommodate the movement in the column, all right? So we're going to get 3 there, right? So we got 3 there, 2 there, and 1 there. So the degrees of freedom will be 6. I have 6 degrees of freedom in the structure. Do you follow? So that's what we're saying, all right? Let's come to the notes now. In general, for structures, they are right. We spoke about that first paragraph. If a joint is free to move in all 3 of these directions, it is said to have 3 degrees of freedom. If it is free to move in 1 or 2 or 1 or even none, then it is said to have 2, 1 or 0. A joint is prevented from having a particular degree of freedom by insertion of a particular support. So fixed support, you agree, we discussed that earlier. There's no degrees of freedom. It cannot move vertically. It cannot move horizontally. It cannot rotate. Okay, and a pin, it allows 1 degree of freedom, which is rotation. A roller will afford 2 degrees of freedom. In other words, parallel to the rollers. Okay, that movement. I'm saying parallel because you could have a vertical roller. This is a horizontal one. All right. So rotation, and here in this case, horizontal movement, and then rigid connection. There's no support there, right? It's just the 2 members being rigidly connected. Then I've got 3 degrees of freedom. What is not mentioned here, perhaps, then we can, you came across this in, what happens if I have a pin? I introduce a hinge there. How many degrees of freedom? How many degrees of freedom? So all I've done, I have removed the rigid connection that we saw earlier. This one here, I took that out and I replaced it with a pin connection. So column, right? And then what I did is I put a connection in here like that with a single bolt going through there. You follow what I'm saying? So now I've introduced a pin. So how many degrees of freedom? Okay, I'm going to
Should
leave
not
it.
be 1, sir.
Well, can it move horizontally still? Anything preventing the column moving horizontally? Think about it. All I did is I took the rigid connection out. There's no support here, right? So there's nothing holding this thing in space. It can move horizontally, correct? Can it move vertically? So remember when you had something like this in analysis? You had a pin support there and you had a pin support there. It was statically indeterminate, right? Okay, so to make it determinate, what happened? You introduced a hinge. Okay, so that's what I'm talking about now. Okay, so can it still move horizontally? Actually, it still has the 3 degrees of freedom. Okay, what it does now is in terms of moment, it's removed the moment connection. So I can't develop a moment anymore. In that structure, I can develop a moment at node 2. In this structure, I can't develop a bending moment, but otherwise I've still got the same degrees of freedom. Anyway, this was just on the side. It just came to mind while we were talking. It's not the focus of our those hinges actually, they are used as analytical tools. That's not very common. Okay, Right, so there we have it. I hope you've understood this first part. Let's look at some examples. Degrees of freedom in a structure. The number of degrees of freedom for the whole structure is the sum of all the degrees of freedom for the joint. So we did the first one, for example, and we said we have 6 degrees of freedom. 1 at node 1, 3 at node 2, and 2 at node 3 gave us 6, right? Let's look at these. Some of them are pretty simple. I've got a 2-span beam. I've got 2 pin supports, right? So support at A is a pin, support at B is a pin, correct? Support at C is fixed. So we're saying A can rotate, there can be rotation about A, there can be rotation about B. At C, the structure is not allowed to move horizontally, it is not allowed to move vertically, it is not allowed to rotate because it's fixed. Are you with me? Okay, so I've got 2 degrees of freedom. Let's move into the second one. So this is covered. Any questions, guys? Just stop me as I am talking, please. A, B, C, D. So I'm looking at this 3-span beam. Okay, here I've got fixity at A, fixity at D. So that is 0 and that is 0. Okay, I've got 1 degree of freedom at B. I've got 1 degree of freedom at C, which is rotation only because a pin doesn't allow horizontal movement, doesn't allow vertical movement, right? A fixed end doesn't allow any movement in 3 directions. Okay, so 2, we're happy with that one. Let's move on to a portal. Very common structures in, very common type of structure, portals. You get the normal rectangular portals, which will always be part of your multi-story buildings. And of course, for industrial ones, we have shapes like that. Okay, so that's very common for industrial ones. Anyway, we deal with that in structural steel in the 3rd year. Okay. Important, it's the basics, building grounds for our 3rd year design subjects. Okay, so here we have a frame which is fixed at A. I'll just take this out so we focus on where I'm writing. Okay, so we're talking about A, B at the top there, C here, and D at the bottom. All right, so A is fixed. How many degrees of freedom? Anything that is fixed, the degrees of freedom are 0. Okay, B is a restrained connection. In other words, a rigid connection between the beam and the column. So it will have 3 degrees of freedom. It can move in 3 ways. C similarly can move in 3 directions. D can only move in 1 direction. Okay, so I add them up and it gives me 7. Right, so I have 7 degrees of freedom as is. If I take it the way it is, that's it, 7 degrees of freedom. Okay, the next one. Sorry guys, any questions? Any questions? Do you have any questions? Have you understood? All right, let's move on to the next one. The next one is a bit more of an elaborate frame. So I've got the same portal, but then I've got a beam sticking out and it's fixed to some point. And then I've got another beam sticking out from that side and it's fixed to a roller. Okay, it's attached to a roller. So here, again, just look at the connections. Any degree of freedom. Let's just label it so we can make a reference to it. Sorry. Right. Let's start with A. Any degree of freedom at A? 0, you agreed, it's fixed. B, 3 degrees of freedom. It's just a rigid connection, right? There's no support there, so 3 possible movement directions. D, 0, so that one was 3. C, 3 possible movements directions. E, 1, because it's a pin, right? And F, 2, because it's a roller, right? So what do I get in total? 3, 6, 8, 9. So very simple, 9 degrees of freedom for the structure. Okay, now that means on the computer, and I was showing some of the students yesterday. Let me just, pick that up quickly. Where's my... when we had the old diploma and we had the BTech, in the BTech students did matrix methods. This will be done in the honors for you guys. Okay. Right. There's a solution for a 2-member plane frame. Okay. These are the matrices that involve. So 1 member, that's just a stiffness matrix. So if I look at 1 member, okay, this is the stiffness matrix for that member, just for 1. So for the second one, I have another one. Then I essentially, what this comes to, and I don't want to go into detail, is you take the stiffness matrix of every member, and then you identify the degrees of freedom. So there's the degrees of freedom, right? Node 2 can move in 3 directions. Node 1 doesn't move, but I have 3 reactions. Node 3 doesn't move, but I have 3 reactions. So I have these 3 unknowns. So these become the unknowns, okay, which I have to solve for. And what we do is we create an equation, which is P minus PF is equal to S times D. So P would be your forces external, PF would be your fixed end moments for something. So some of those, so what we're saying is, for example, here in this particular structure, I had a load, which is fine. That will give me the forces, but I also had a fixed moment, which was applied to the node directly, not the beam or the inclined member. So that's where the PF comes in, okay, is equal to S. S is the stiffness matrix at that connection times D, which is the number of displacements. And then you work out the displacements, and here it tells me the displacements. Number 1, which is horizontal, is 0.5 millimeters. 2 is the vertical, and so this one, that's a positive direction. So it means it's actually that way, okay, because that's way is positive. I've got minus 0.00135, so that means it's going down. Okay, and it's going down by 1.35 millimeters. And then I've got a rotation, and that rotation is anti-clockwise because that's the way the program works. And that rotation is 0.029 radians. Okay, so what I'm saying to you is, the first thing that I had to do when starting this analysis, right, was to actually check or determine where the displacements are. All right, so that was the crux of getting the solution, the first part. And then the other parts just come in place. All I did here at the end was, these are the answers from the matrix method. And of course, the computer uses the matrix method. So I just wanted to check and show that I get the same answers or very, very similar answers. Okay, so this is something that is done at a little bit of a higher level. But we will see something very similar. We use a method called slope deflection, and in there we have to start by identifying the unknowns, and the unknowns are displacements. Okay, so we have 3 methods that we're going to use. Moment distribution, where we don't have to worry about displacements. Slope deflection, where we start with identifying the displacements, and the third one is virtual work, which again is a bit different, and I don't want to create any confusion with that one right now, so we'll talk about that later. Okay, so any questions then on that? Right, I'm just trying to highlight why this is so important. So the computer uses this approach, right? Now, if we're doing these calculations by hand, can you imagine doing a, so you've got 1, 2, 3 here. You got 1, 2, 3 there, unknowns 2 there, and 1 here. So you've got 9 unknowns. In other words, you're going to have a matrix which is 9 by 9. Do you understand what I'm saying to you? Sorry. So you're going to have 9 columns and 9 rows. Do you follow? And now can you imagine solving that by hand? It could become quite cumbersome. You agree? Okay. So if we had something and we want to make it simpler. Okay. So simplification for manual calculations. Well, what do we know? What we know is that these members that we have. So let me take a very simple one. If I have a column, okay, and it's pinned at the top and it's pinned at the bottom, and I apply a load to it, okay, all right. If I use something like the ruler that we use, the plastic ruler, okay, we'll see that that just bends like that correctly, okay. And if this is allowed to move, if I have a vertical roller here, for example, if I have this situation, right, that's going to move down, so I'm going to get some settlement delta. Okay, now if I take something that is very, very rigid, okay, so now you can think of your triangular ruler, your scale rule that you use, for example, and now I load this. The difference between this is that you're going to get negligible. The movement here is going to be almost equal to 0, nothing, very, very small, okay, because I've got something very rigid. Give me a second, I hope this video thing works. Let me pick it up and show it to you. 1 second. Okay, let's see if we can get the video. Not the video, the camera on here, sorry. So you can see what I'm referring to. The camera on, can you see me? Okay, so what I'm saying to you is, here's the normal plastic ruler, right? Very, very flexible. So if I hold it at the bottom and I put a load on the top, you can see that I'm going to get a movement, right? However, if I take this ruler, holding it at the bottom, apply a load at the top, and nothing significant happens. I don't get any buckling or anything of that sort, okay? So, right, so this is what we're talking about. So we're talking about something that is very, very stiff, right? Let me just put that camera off. Wait a second. Okay. All right, we're done with that. So point that I'm trying to make is I have infinite stiffness, right? A times E. In regular computer analysis of structures, the identification of degrees of freedom is one of the first steps that is carried out. If it is of no particular relevance to the computer how many degrees of freedom, right? Because it can solve any amount. However, when we do it in manual calculations, we find that for each lateral degree of freedom in the structure, we have to carry out a large amount of additional calculations, okay? We therefore prefer to make simplifying assumptions which reduce the number of degrees of freedom. Okay, that's not DOT, it's DOF, right? To the minimum possible. We assume that all of the members have infinite axial stiffness. So that's our assumption, right? We're dealing with something like I showed you there in the screen and not like a bean bag, for example. That is, they do not extend or compress when subject to tensile or compressive forces. Whilst we know that this is not true in practice, it turns out that since flexure is the dominant type of action in the kind of structure studied here, the error induced is marginal and the assumption is found to be reasonable. What we're saying is that the way we apply loading to our structures and the way we formed our structures are primarily in bending. So using that, we get very small rotations or shortenings or elongations. Okay, so then that is why we can say that our stiffness, we have almost infinite axial stiffness. Referring to the third example above and applying this assumption, it will be seen that since both columns are fixed at their bases, so we come into this one here, right? So we're looking at this one again, the third one that we dealt with. So what we can see is that if this has infinite stiffness, these two, they have infinite stiffness, even the beam, then because the column is connected to a foundation, it's not really going to expand or shorten because this thing's not really going to change its length. The same thing applies here, right? I've got a pin connection which prevents it moving vertically. It can't happen, right? So that prevents the movement at the top really because this thing is not really changing in its shape. If you follow what I'm saying, it's not really expanding too much or contracting or getting smaller, right? So I don't get the vertical movement. So I can actually, this is so small, I can take it out. Right, so that's 2 I can get rid of. And then that means my n will change to 5. So I have 2 degrees of freedom which are removed. This negligible, can be ignored, and therefore I reduce the unknowns to 5. Okay, and then the next thing is, if I look very carefully, so if the structure were applied a load to this thing on this side, I would get a deflected shape which looks like this. We do this deflected shapes when we get to qualitative analysis. Chapter 3, which I didn't give you a print of, I'll give you that in the classroom. And I put it up on Teams yesterday, but when we do that qualitative analysis, we don't do it with numbers. We look at what happens if I apply a load, what happens to the structure based on various things, and we will get something like that. All right, so what we're saying is, here we end up with no vertical real movement, but rotation happens. So let me just make this a bit bigger so you can see what I'm talking about. So what I'm saying to you is there's a rotation that is taking place, for example, between there and there, there's an angle change, okay? There's angular change here as well. They would have to be because that would have to remain at 90 degrees, okay? Right, and then there's horizontal movement, obviously, which you can see was the distance that moved from there to there, or the distance that moved from there to there. You follow? Okay, so there's horizontal movement. So that's what we're saying is, now, when we take the horizontal movement into account, we've got a rigid member on the top. So basically, again, sorry if I can just show it with my, I'll show you a model when we get to the classroom, okay? But just quickly with the camera. Just quickly on the camera. All right, so what I'm saying to you is, look at this. There's my portal. This scale rule, okay, is now my beam. So if I move it laterally to one direction or the other, can you see that the length is not changing, which means the deflection at both ends has to be equal. Okay, so that's what we're alluding to there. So if I come to that one, so I'm saying, sorry, let's get this thing back to full screen. So we're saying I could reduce this by 1 more because those two will then be equal. So I've got delta and I've got delta. So I'm saying n what could be called 4 now because the 2 deltas are equal. Are you with me? So I could make it from 5, or I can even reduce it to 4. Let's look at this one. I've removed the verticals. I took them out and it makes sense. They don't exist because of this one and because of that one at the bottom. It won't allow vertical movement. Okay, horizontal I can take out because although I have a roller here, Okay. Unfortunately, we don't have a roller on the left-hand side. So this thing can't move because of the fixity here. And these are region members. Okay. Therefore, that's gone. All the horizontals are gone. So all the horizontals are taken out. You follow? So that way I've removed 4 already directly, and this one as well. So even this was a roller, it can't happen because it's attached to a fixed support at the other end. Got it? So I'm able to remove 5. So from the 9 minus 5, I've got it down to 4. So what I would like you to do is please attempt the following for next week, and we will talk about this one. I just want to confirm you are the A group, A1, is that right? Your lecture is Monday. Your lecture is on a Monday, and I'm just trying to see, are you the Monday group or 1 second? Sorry, guys. Okay, so you guys are on Tuesday, not Monday, right? Okay, so that you've got a double day, so we'll have to continue on Tuesday. I was hoping you could give me, no, leave it. Let's leave it for next week. It's fine. We'll be in the classroom then. A lot easier, hopefully. Okay, so please attempt this. Okay, please attempt this tutorial. All you have to do is put down the degrees of freedom. So draw the degrees of freedom and then add them up and say, for this beam, it's so much. For that one, it's so much. For that, etc. Okay, right, we'll stop there. Let's stop at that. Okay, and we'll meet again on Tuesday. Right, if you have any questions, you can come to the office and see me. I'm here between 9 and 10 today.